Hello! In this video, we are going to prove the following proposition. The sum of two natural numbers is also a natural number. Okay, so the way that we can think about this statement is we can think of it as though we're trying to prove for all natural numbers n, we have for all natural numbers n plus m is a natural number. So really, if we can prove this statement, then that will mean we have proven the proposition. Now, in reality, this statement is logically equivalent to if we instead had for all natural numbers n, we have for all natural numbers n plus m is a natural number, right? It doesn't really matter if you swap these two around because they're logically equivalent. However, for us, it'll be more convenient if we prove this version. Now, we're working off of Tau's analysis, and the way he defined addition of natural numbers is as follows. For any natural number m, we define 0 plus m to be m. And for any natural number n, we define n plus m to be n plus m plus plus. Right, and we're going to be explicitly using one of the axioms for natural numbers that he wrote, which was axiom 2.2. If you recall, it stated that the successor of every natural number is also a natural number. Okay, so now let's get into proving the proposition, which means we're going to be proving this statement. And we're trying to prove a statement about every natural number. So give me an arbitrary natural number. I'll call it n. And with this arbitrary natural number m, our goal is to prove for all natural numbers n plus m is a natural number. And we're trying to prove a statement about all natural numbers. So what we can do is we can use induction. So really, we're proving this statement by mathematical induction. So let's start with the base case. Now, if you recall, in the base case, we're trying to prove that this statement is true in the case where our natural number n is 0. So really, we're trying to prove that 0 plus m is a natural number. Now, by our definition of addition, we know that 0 plus m is equal to m. And by our assumption, m is a natural number. So, 0 plus m is a natural number. And that's exactly what we wanted to prove in the base case, right? We wanted to prove that this is true in the case where n is equal to 0. Well, we did. We proved that 0 plus m is a natural number. So this completes the base case. Now let's move on to the induction step. Now in the induction step, if you recall, we give ourselves an arbitrary natural number n, where this statement is true. So give me an arbitrary natural number n and assume n plus m is a natural number. And remember, the goal of the induction step is to prove that this is also true for the successor of n, right? We know that n plus m is a natural number, but now we want to prove that n plus m is also a natural number. That's how we complete the induction step. Now, from our definition of addition, we know that n plus m is equal to n plus m plus plus. And here is where we use our axiom 2.2. Remember, if n is a natural number, then the successor of n is also a natural number. So applying this axiom into our proof, since n plus m is a natural number, it follows that n plus m plus plus is also a natural number. So n plus m plus plus is a natural number, which means n plus n is also a natural number. And that's exactly what we wanted to prove in the induction step. So this completes the induction step. So we completed all parts of the induction, which means we have successfully shown that for all natural numbers n plus m is a natural number. So what do we have at this point? Well, we have an arbitrary natural number m, and from there we are able to deduce that for all natural numbers n plus m is a natural number. Since m is an arbitrary natural number, this means for all natural numbers m, we have for all natural numbers n plus m is a natural number. So we have precisely proven this statement, which amounts to proving the proposition. And so this completes the proof. And so yeah, that's pretty much it for this video.